Hi guys, welcome to the second part of the explanation of the uniform circular motion. Okay, so this is the second part of the theory. If you remember in the previous video of theory, we saw these formulas: the angular displacement, the angular velocity, the tangential velocity, and another equation for tangential velocity. Okay, so I just want to mention that these two equations, for example, the angular displacement is a displacement in a circular motion. How many radians did I move? Angular velocity, how many radians per unit of time? Okay, so these two are circular units, circular motion. Okay, and these two over here are for linear motion. So if they are gonna be in linear motion, their units are gonna be, for example, in tangential velocity are gonna be meters per second, and for this equation and also for this equation. Okay, so if you remember in the previous video about the 5 cyclists, okay, we saw that the further, for example, with this equation, remember that all of the cyclists had the same angular displacement. Okay, but according to this equation, depending on the radius, they were going to have different tangential velocities. Okay, so that's it. If, well, the further the radius, or the greatest the radius, or the further the cyclist is from the center, the more tangential velocity is going to have. So it's going to have more linear velocity. Okay, but remember, those cyclists cover the same angular displacement and they had the same angular velocity because they reached the goal at the same time. But of course, one of them, the fifth cyclist, was going to have more effort in order to reach the goal at the same time. Okay, so remember that we mentioned that the tangential velocity was perpendicular to the radius. Okay, so I'm going to draw it over here. So this is the tangential velocity at one period of time, and then we're gonna have another tangential velocity at some other point. Okay, so if you remember from the first video, remember that a vector is a physical quantity, and that physical quantity must have a magnitude and direction. So vector has magnitude and direction. Over here I'm going to write it direction. Okay, so let's suppose that the tangential velocity for the fifth cyclist, let's say that the tangential velocity for that fifth cyclist was going to be, I don't know, 5 meters per second. Okay, so the fifth cyclist is going to have 5 meters per second the whole track. Okay, well, in this case they just traveled 5/6 of the revolution. If you remember, that is an information that comes from the previous video. So that is the tangential velocity. Okay, and if you see, well, we mentioned in the previous video that it was going to be a uniform circular motion, so the velocity remains constant. The angular velocity is constant and the tangential velocity is constant. So that means that the velocity of the fifth cyclist is the same all the way. But if you see, the definition of a vector is magnitude and direction. So the magnitude remains constant. But what about the direction? If you see here at this period of time, I got this direction over here. It's kind of 90 degrees. And then in another moment, the direction change and it's like between 90 degrees and 180 degrees. Okay, and we can see that better in this video, and I'm gonna give you the chord over here. So if you see, that white line is the velocity. Okay, that white line is the velocity, and if you see, is changing. The direction is constantly changing. Okay, I repeat, the magnitude is the same, but the direction is going to change, just as it says here. Magnitude is constant and direction is changing. So if there is a change in direction, that means that we are going to have an acceleration. Remember that the acceleration produces a change in velocity, but not in this case. Um, it will not have a change in magnitude. It will be a change in direction. Okay, and that concept is called centripetal acceleration. And okay, so in the video they're gonna say it. Okay, will be an acceleration, and it's called centripetal acceleration. Okay, so I'm gonna write it. AC equals centripetal acceleration. Okay, and that is an acceleration that points to the center. That is the definition of centripetal. Okay, points to the center. Okay, so in my drawing that I got over here, I'm going to, with another color, I'm going to draw the acceleration, the centripetal acceleration, and it is this one over here, centripetal acceleration, and in here I got centripetal acceleration. So all the way, all the motion, there is going to be a centripetal acceleration. Okay, so that acceleration is going to be responsible for changing the direction of the velocity. So we could say that that is the responsible one, that you don't go and you don't fall, so you continue with your motion. No, you are stuck in a circular motion, and you are always attracted to the center due to the centripetal acceleration. Okay, so what is the equation for centripetal acceleration? Okay, so the equation is going to be tangential velocity raised to the square over the radius. Okay, that is the equation. So what about the units? Well, let's see the units. For tangential velocity, we got meters per second, but both are raised to the square, and radius, the units are going to be meters. So if I do outside with outside, inside with inside, so I'm going to have meters square over meters times second square. So I'm going to cancel meters with this square. So the units are going to be meters per second square. Okay, so I'm going to circle this, and I'm going to call this as my 1, 2, 3, 4, fifth equation. This is going to be my fifth equation for circular motion, and the units for the centripetal acceleration are meters per second square. So you need to look at the units. Meters per second square is a unit for linear motion. Remember that the units for circular motion are going to be degrees or radians per second or degrees per second. But if we got meters per second or meters per second square, that motion or that measure is going to be for linear motion. Okay, now I can have another equation for centripetal acceleration. If you see, this is a tangential this is the tangential velocity, so I can substitute the value of this equation over here. Okay, so I can have another equation. So centripetal acceleration equals the value of the tangential velocity, that is the angular velocity that multiplies the radius raised to the square over the radius. So it's going to be w squared times radius squared over radius. So I'm going to be cancel this with this. So the next equation for centripetal acceleration will be angular velocity raised to the square times the radius. And the units are going to be exactly the same, meters per second square. So I'm going to circle this one. And I'm going to say that this is my sixth equation. Okay. Now, if you see, well, I got the equations for acceleration. So remember, if there is a change in velocity, that means that I got an acceleration. And if I have an acceleration, there must be something that produces that acceleration, okay? So that thing that produces the acceleration, remember that is called force. So in this case, yeah, I'm gonna have a force, and it's called Fc, centripetal, centripetal force, centripetal force, okay? And the name centripetal means that exactly the same. It points to the center or towards the center, okay? So if I return to my drawing over here, and I can use another color, let's say I'm gonna use this color over here. Okay, I'm also gonna have FC, okay? FC, centripetal force, and that force points to the center and is the responsible that you don't fall or you don't go away, because that force points to the center. Okay, so you can be stuck in a circular motion. So what is the equation for centripetal force? Is exactly the same. Centripetal force equals mass times centripetal acceleration. Remember the units. The units for mass are kilograms and the units for acceleration are meters per second square. So that means that I'm going to have newtons as units, okay? It doesn't matter if they are going to be linear forces or centripetal forces or something like that. The units are always the same. And this is my equation number 7. Okay, number 7. Of course, I can have more, another equation for the force, because, well, centripetal acceleration is tangential velocity raised to the square over the radius, or angular velocity square times the radius. So if you see, I can have two more equations, but I'm just going to use one more, okay? Centripetal force equals mass times acceleration, and I'm going to use this equation over here. So it's going to be times W, that is the angular velocity raised to the square, times the radius, okay? So I'm going to circle this equation over here, and that will be the equation number 8. And those are going to be the same units, but remember, mass is going to be in kilograms. The angular velocity is going to be in radians over second, and the radius is going to be in meters. Okay, so now I got tangential displacement, angular velocity, tangential velocity, centripetal acceleration, and centripetal force. So if you remember, well, I got all the equations just as the equation that I had for linear motion, okay? But before we finish our explanation of uniform circular motion, it is important to mention two more concepts, okay? One of those concepts is the frequency, okay? Frequency. Frequency is, the letter for frequency is an F. It's like an italic F. So this is frequency. Frequency, and the definition is, so we can see some examples of frequency, number of cycles per unit of time. So let's write some examples. Frequency, okay, so let's say that I can do, for example, 10 laps. I can travel 10 laps. Let's say that the lap is going to be a park or something in a circular form, in a circular shape, sorry, in 30 minutes. Okay, that is a frequency. 10 laps in 30 minutes. Okay, one another equation. Well, I can have 100 reps in 1 minute. Okay, and this is equal as 100 RPMs. Remember the car dashboard, the speed or the revolutions of the motor. Okay, so that will be 100 revolutions per minute. Okay, and we also can have 60 cycles in 1 second. Okay, so for example, frequency, if you see, we got minutes, I got seconds, I could have hours and so on. But what are the official units for frequency? Okay, the official units for frequency are hertz. Okay, so this means hertz. Okay, so what are the hertz? They are cycles per seconds, number of cycles in just 1 second. So if you see, well, if I want to write these frequencies in hertz, well, I need to transform minutes and in seconds. Okay, so for example, this one is already in cycles per second. Okay, so this one over here will be frequency equals 60 hertz. Okay, 60 cycles in 1 second. And if you know, that is the frequency for alternating current. I don't know if you are going to see it later, if you are going to study engineering, electrical engineering or something. So this is a concept that is going to be very common. Okay, so there is another concept that is called period. Okay, T equals period. Okay, so what is the definition for period? Okay, it is the time that takes a body or something that takes to complete one cycle. Okay, so I can ask you, what is the period, the rotation period of the Earth? Okay, so the rotation period of the Earth, you can say that is 1 day, or you can say that is 24 hours. Okay, but and it's correct. I mean, that's the period, but the official units for periods are seconds. So the period would be how many seconds do we have in 1 day. Okay, so it's going to be 86,400 seconds. Okay, that is the rotation period of the Earth. Okay, so we have two more equations that says that the period equals 1 over the frequency, and also frequency equals 1 over the period. Okay, so I'm gonna circle these two equations. So this means that if you have period, you got frequency, and vice versa. So I'm gonna write that this equation is the number 9. This is the equation number 9. Okay, number 9. And for example, let's see the previous example of the frequency of 60 hertz. Okay, frequency equals 60 hertz. Okay, that is the number of cycles in 1 second. But what if I want to find the period of that object? Okay, so let me open my calculator that is over here. This one. Okay, So what is the time, the period? Is the time that takes to complete one cycle, okay? So let's see, it's going to be 1 over 60. I can use this 60, and I can use this key that is going to be raised to -1 using the law of the exponents. That will mean that it's going to be 1 over 60. So I'm going to press equal, and that is the period, 0.0166 seconds. Okay, so this particular case is going to take 0.0166 seconds in order to complete one cycle or one lap or one rep. That is absolutely fast. Okay, it's fast, really fast. Okay, so before we finish, if we see, we have seen a lot of information in this video. Okay, so let's see the last two equations that we are going to see. Okay, so I'm gonna write this W. Do you remember what is W? W is angular velocity. Angular velocity is displacement over time. So how do you translate this? Is the number of radians per unit of time, is how much you displaced in unit in per time unit. Okay, let's say that I travel a circle. Okay, my angular displacement was a circle, but remember that the angular displacement must be in radians. So how many radians is a full circle? Do you remember the video, the previous video? I just put you a table that said one circle equals one lap equals one rep and so on. Okay, that is 360 degrees. Okay, because a circle is 360 degrees. So how many radians is a circle? Is 2p radians. Okay, 2p, and I'm gonna circle this. 2p is a cycle. Okay, so the angular velocity is angular displacement over the time. Okay, how much time does it take to complete one cycle? Well, I already defined it. Time that takes to complete one cycle. So I'm going to substitute this t that is for time, and I'm going to substitute for t, this t, because that's the period. So this is a cycle and this is a period and this is the period. So the next equation that I'm going to have for angular velocity is going to be angular velocity equals 2p over period, over the period. And I'm gonna circle this equation over here, and that will be the equation number 10. The units are gonna be the same. The units are radians per second because period, the units for period are seconds. Okay, I didn't mention, but well, yeah, I mentioned the units for period are seconds, official units for period. Now, if you see, the period is in the denominator, just as this equation over here. Period is in the denominator. So, for example, I can have this. Angular velocity equals 2 times p times 1 over t. Okay, I just separated. Okay, so how much is 1 over t? That's frequency. This is the equation. So the next equation that I'm going to have for angular velocity is going to be 2p times frequency. The units are going to be the same, radians per second. Okay, and remember that the units for frequency must be the official units that are hertz, cycles per second. Okay, so this is going to be the equation number 11. And guess what? This is the complete explanation for the uniform circular motion. In the next videos, we are going to use all these equations in order to solve problems. And I promise you, well, and I hope that you can see that it's not that difficult as it seems. Okay, so I hope I see you in the next videos, guys. Bye bye.